coffee cup calorimetry. We're actually going to do this in lab. It's so fancy. So it's literally 2 styrofoam coffee cups, right? And you use 2 nested inside of each other just to give you a little bit more insulation. And there's a lid on top. This one looks all fancy. It's a loose-fitting cork lid. What we have are actually squares of cardboard with a hole poked in them for the thermometer. And I think most of those squares of cardboard are older than you are. So like they're vintage cardboard, right? But it turns out you can do a pretty decent experiment using 2 coffee cups and a piece of cardboard instead of that fancy bomb calorimeter with a stirring mechanism and little airtight bomb in the middle and everything. So this works really well for aqueous, aqueous reactions. This is constant pressure calorimetry. So the pressure is not going to be changing because it's open to the atmosphere. And like we mentioned earlier, a lot of times we don't care about any pressure volume work because it's so small, it just doesn't really matter. So what we've got going on here is we're going to use Q equals MC delta T. Q for the solution is equal to the mass of the solution times the specific heat capacity of the solution times the change in temperature. We can measure the change in temperature of the solution. We can measure the mass of the solution. The specific heat capacity is usually very close to that of water, but that can also be measured. And so we can calculate Q for the solution. That's the heat absorbed or lost by the solution. What's the other part of that? The other part of that is the chemical reaction. So the chemical reaction, which is what we're interested in, we're interested in delta H for the reaction. The heat gained or lost by the chemical reaction will be the same number as what is lost or gained by the solution. It'll just be opposite in sign. And here we're assuming that our coffee cup is perfect and we're not losing any energy to outside of the coffee cup. Okay, so Q reaction is equal to Q at constant pressure, which is equal to delta H for the reaction. Generally, we want delta H in kilojoules per mole or joules per mole. And so we'll take this Q that we calculate, and we know how much stuff we put in for the reaction. We can calculate the moles, and we'll divide by the moles. Okay, any questions? So here's an example. The addition of hydrochloric acid to a silver nitrate solution precipitates silver chloride according to the reaction, blah, blah, blah. When 50 milliliters of 0.1 molar silver nitrate is combined with 50 milliliters of 0.1 molar HCl in a coffee cup calorimeter, the temperature changes from 23.40 degrees Celsius to 24.21 degrees Celsius. Calculate delta H for the reaction as written. Use 1 gram per milliliter as the density of the solution and specific heat capacity of 4.18 joules per gram degrees Celsius. Okay, so there's a lot of numbers in here, lots of words. Let's just highlight those numbers because that's what we've been doing. And then what we're trying to find is delta H for the reaction. So coffee cup calorimeter. So what we got here is our coffee cup, and we've got a solution in there, right? So what's inside of that? What's the volume of what's inside of that? We've got 50 mils of this solution and 50 mils of the other solution, right? So we have 50 mils plus 50 milliliters, or 100 milliliters of liquid in our coffee cup. We want to calculate Q for the solution. That's going to equal M for the solution times the specific heat capacity for the solution times the change in temperature for the solution. And that's going to equal negative Q for the reaction. They didn't give us a mass, did they? But they told us the volume of what was put in here, so we can figure out the total volume, and then they gave us the density to use. So if we take 100 milliliters, we can convert that to a mass. Again, don't use the density equation. Just think of this as converting units. I want the mass, so I'm going to divide by milliliters. I go and I look at the density, 1 gram. So 1 gram per milliliter, and so this is 100 grams. So that was not given directly in the equation, in the problem, but that is the mass of the solution. That make sense? So we also need specific heat capacity of the solution. Okay, so they gave us that. And we need change in temperature for the solution. Well, we can calculate that, right? Delta T for the solution, whoops. Solution does not start with an F. That will be the final temperature, that's where the F came from, minus the initial temperature. So here we're given the temperature change from this to that. So I'm going to take the final temperature and subtract the initial temperature. And sometimes when we're doing relatively simple subtraction like this, some people like to do it in their heads. Oh, that's great, but always double check, because it's a shame to get a problem wrong when you did some simple math wrong. So there's my delta T. So I have delta T, I have M, and I have the specific heat capacity. So I can calculate the amount of energy, the amount of heat gained or lost by the solution. From the temperature change, is this gaining or losing energy, the solution? It's gaining because the temperature is going up. So the solution's gaining heat, that heat is coming from the reaction's losing heat. Yeah?
So if the delta T was a negative sign, then that means that it would be losing.
Right, if delta T was negative, that means the solution is cooling down, it's losing energy, that energy is going into the reaction. Yep, good question. So Q for the solution is the mass times the specific heat capacity times the change in temperature. So 100 times 4.18 times 0.81. My calculator says 338.58. If I'm looking at units, the grams are going to cancel, and degrees Celsius are going to cancel, and so I'm going to end up with joules. So we're almost there, but we're not quite there. So this is the amount of heat that was gained by the solution in this particular experiment. When it says delta H for the reaction as written, that means for this chemical reaction, for molar amounts. So for 1 mole of silver nitrate reacting with 1 mole of HCl, what would delta H be? So we're not quite to that yet. So we're looking for this up here, delta H, the reaction. So this was Q for the solution, right? And now there's just not really enough room here. So that means Q for the reaction is equal to negative Q for the solution. So Q for the reaction is going to be negative 338.58 joules. And of course that's too many sig figs. We should only have 2 here. How many moles of silver nitrate reacted to have that energy change? How can we figure that out? Well, how many moles of silver nitrate were put into the cup? We've got a volume here, and we've got a molarity, right? So this is moles per liter, and this is the volume in milliliters. So I had 50 milliliters. I can convert that to liters. And then I can use the molarity. So I want moles here because I'm trying to get to moles, and liters on the bottom. So there's 0.100 moles per liter. So that's 0.005 moles. How many sig figs does that number have right now? 1. How many should it have? 3. How do I give it 3 sig figs? I need to add zeros at the end. That's the hardest thing to remember. When you've got lots and lots of digits, just pulling out the correct number of them, not so much a problem. But this happens a lot. The calculator doesn't put those zeros in, and so you just type in what your calculator says, and on the My Open Math lab reports, it gives you a red check because you don't have enough sig figs. So watch out for that. So that's the moles of silver nitrate. The 50 milliliters times the 0.1 moles per liter. How many moles of HCl were in there? The same, right? We don't even have to calculate it because it's the same volume and the same concentration. So when we do the same calculation, we'll get the same number, right? So that's equal to the moles of HCl. So 338.58 joules of energy were given off by the reaction when 0.005 moles reacted. We want to know how much is given off when 1 mole reacts. So we're going to divide. I did not mean to do that. It's just getting a little too crowded. I'm going to take out that part. So negative 338.58 joules for every 0.00500 moles. And that's going to give me units of joules per mole. So I take my 338.58 and I divide by my 0.005. Well, it would be helpful if I put in an operation there. And my calculator is showing me 67716. The units then will be joules per mole. And I forgot the negative sign. How many sig figs should it have? 2. Because our Q only had 2. And that had 2 because of the delta T. So 67,000 is a pretty big number. So normally what they'll do is they'll convert this to kilojoules. So let's take care of that. I want joules in the bottom and kilojoules on top. Kilo means 10 to the 3. So then this is going to be negative 67.716 kilojoules per mole. And that's a lot safer to be rounding, right? Because we want to round to 2 sig figs. We look at the next digit, it's 5 or greater, so it rounds up. So this is going to be negative 68. Negative 68 kilojoules per mole. Yeah.
So, I don't know if you explained it already, but why is Q reaction negative Q solution?
Okay, why is Q reaction equal to negative Q solution, or Q solution is equal to negative Q reaction? They're the same. That kind of messes with people sometimes. But if I take this piece here and multiply both sides by -1, I get this guy down here, Q solution is negative Q reaction. So one is losing heat, one is gaining heat. So the numbers are the same, the signs are opposite. Okay? Good question. That makes sense? That's something that messes people up. I wish I could come up with a better way to explain it. Yes? Why do we go to joules per mole? Another good question. Well, this is saying calculate delta H reaction for the reaction as written. So what you'll typically see, like if you look this up, well, what's delta H for this reaction? You'll see just the unit kilojoule. But delta H it depends on how much stuff is reacting, right? If you react more stuff, you get more heat change. So we have to specify how much stuff is reacting. And so the standard is delta H refers to the chemical reaction where we're looking at amounts in moles. So this is 1 of this, 1 mole of that, reacting with 1 mole. They don't usually say per mole here because what if you had a coefficient of 2? If you had a coefficient of 2 here, that would be negative 68 joules for every 2 moles of this. Okay? Good. Yeah, so what would we do here if there was a coefficient of 2 here? And let's pretend the HCl there was just plenty of, and that I'm not going to mess with that. So this would be per 1 mole of silver nitrate, and delta H would need to be per 2 moles, so we'd have to take this and multiply by 2. And I don't think there'll be anything on an exam, especially where I'll try to trick you with something like that. Any other questions? Yes?
Why do you divide by 0.005 and not add both of the moles together so you get?
Well, that's a great question. So why did I divide by this number 0.005 when I had 0.005 moles of this one and 0.005 moles of that one? Why not add them together? Because we're looking at each of these separately, okay? So this is the amount for 1 mole of that and for 1 mole of that, not for 2 moles. Does Does that make sense? Yeah.
So if it was two different values for the moles, then we would just put, like, we would just name which one it was?
Okay, so what if there were two different amounts? What if this one, let's just change this up. What if, oops.
I just mean, like, would the answer be written differently? Would it be like,
Well, there's a couple of different things to think about here. What if we calculated and there was 0.005 moles of the silver nitrate, but there's 0.015 moles of the HCl? Then we would have to identify the limiting reactant. Because even though there are more moles of this, they're not all going to react, right? Only this many can react, and so it'll still be divided by 0.005. And that's not something that we'll do to you. This one, they had to give us the volumes of both because we needed to calculate the mass of the solution. But they were very kind to us, and they gave us the same moles of each, so we don't have to worry about that. In the experiment we're going to do, not today, but the solid that's being added is the limiting reactant, and we're not even going to look at moles of anything else. We'll just have the one thing. And we don't need to know what the volume is because we're going to actually put the silly thing on the balance and weigh it, right? Any other questions? Let me return this to what it was. Those were great questions. Minus 68 kilojoules. The same reaction with the exact same amount of reactant is conducted in a bomb calorimeter. Okay, I started off that one wrong. I thought it was referring to the previous problem. It's not. Some other new reaction. We're going to do a reaction in a bomb calorimeter and in a coffee cup calorimeter. For one of these, we're going to get Q is negative 12.5 kilojoules. The other one's going to give us, the other one, come on. Good grief. The other one's going to give us negative 11.8. So which is which? Yes. The coffee cup calorimeter can have a change in volume, right? And it says, assume that the reaction has a positive change in volume. So for the coffee cup, we've got heat and work. And the work is equal to negative P delta V. So we've got Q minus P delta V. So if delta V is a positive number, then we're going to be subtracting some energy from the heat, right? We go, change in energy here. Does that make sense? This one's kind of weird. Notice these values are really close to each other, aren't they? There's not a huge difference. But in the bomb calorimeter, the volume cannot change, and so no work can possibly be done. So you're going to get just Q, because W has to be 0 because delta V is 0. In the coffee cup, the volume can change, and the pressure is going to be some positive number, and this is some positive number. So we're going to end up subtracting. So delta Q for the coffee cup should be bigger or smaller than the other one? So for the coffee cup, we've got this, and for the bomb, we've got it just equal to Q. So if I'm subtracting these, is that going to make delta E bigger or smaller? Smaller. Okay. Yeah. Yeah, I was thinking about that. I didn't necessarily write that in the best way. Maybe this would be better. Q plus, and this is negative P delta V. I don't know if that's clearer or not. So the work is a negative number being added to Q. Makes it smaller, just like subtracting a positive. So they're asking which one is the bomb calorimeter, so that one's going to be the bigger one. This is a very minor point. We don't use bomb calorimeters in Chem 1A, they're too expensive. Any questions? Okay, so it turns out that I screwed that up. This would be true if Q was positive, but as my wise student pointed out, Q is negative, right? So Q is negative here, and then we're adding more negative, that's going to be bigger. But we're adding a negative to a negative.
Yeah. Well, the numbers are going to be bigger, but it's still going to be smaller because it's losing more energy, right?
Yeah, so that's another perplexing thing. Which is bigger, negative 13 or negative 12? Negative 13 is bigger. Because the negative is just telling us what direction things are going.
Oh, okay.
The bigger one is the one that's farther from zero. That's not confusing at all, is it? Not confusing at all. Yeah. Okay, so I got that one wrong. So that one's going to be the bomb calorimeter. Because, so Q is 11.8 kilojoules, and then we're adding negative P delta V. They don't tell us what that is, but this is a negative number. And so this is going to get more negative, so that could end up being negative 12.5 kilojoules. And if that's the case, we can actually figure out what that is. This one must be 0.7. So negative 11.8 plus negative 0.7 gives us the negative 12.5. I think I might just skip this example in the future because I don't think it was worth all the time we spent on it. And I think I killed some brain cells. Sorry about that.